Hello everybody, this is Dr. Christopher White, and in this presentation we're going to continue thinking about volcanoes and volcanic hazards. So the next thing we're going to think about is what controls the style of eruption which a volcano produces. So this is going to correspond to section 6.2 of your textbook. So what we can see here is we have four images of different situations associated with volcanic eruptions. So the first image we have up here is one that's probably familiar to us. This is an image of a lava flow. So we've got to think to ourselves, what's going to be affecting the lava flow? And of course, it's going to be a reflection of the type of lava being erupted. What's its chemistry? So we know that mafic lavas are naturally going to be quite hot, and we know their viscosity is going to be quite low, and as such that will allow the lava to flow away from the volcanic vent and produce lava flows which can spread out in some cases over hundreds of kilometers. In contrast, a felsic lava is naturally going to be cooler and it's going to have a higher viscosity, and so this means the lava will be unable to flow anywhere near as far. So the extent of the lava flows which are produced by the volcano are going to be controlled by the type of lava being erupted. So another feature that we see sometimes associated with volcanoes is something which is referred to as a lava fountain. And these tend to be associated with mafic volcanoes. So we'll tend to see them associated with cinder cone volcanoes and shield volcanoes. So what we have here is we have the early stages of a mafic volcanic eruption. And in these early stages, the lava that's coming out onto the surface of the Earth contains some volatile. So it's got some gas dissolved in it. And so what happens is as the lava approaches the surface, the gas starts to come out of solution. There's a volume expansion as all these gas bubbles start forming, and that pushes the lava out of the volcanic vent under very high pressure. And so it sends the lava shooting into the air, producing the fountain. And what you can see is this lava being thrown into the air is essentially splitting up into lots and lots of clumps. Okay, and these clumps will consist of mafic lavas which cool down in the air. They'll be full of vesicles, so they'll be, they'll look like Swiss cheese. And this is this very highly vesicular mafic volcanic rock which we refer to as scoria. And so each one of these pieces of rock is going to be a piece of scoria, so it's going to be very, very vesicular. And this is going to build up around the volcanic vent, and it's going to form a cinder cone style volcano. So the next feature that we can see here is a volcanic dome, and these are associated with the high viscosity lavas especially, so felsic lavas, very, very sticky, lower temperature lavas. And of course, as we've discussed, the lava will be unable to flow a great distance from the volcanic vent, and so it just piles up around it. So underneath this dome here is going to be the main vent where lava is being extruded, so it's being pushed out. But you'll notice there is no obvious lava flow, so we can't see anything like this coming out around the side of the volcanoes, and that's because the lava is being pushed into the interior of the volcano where it's cooling and solidifying because it can't flow very far. Then what happens is the next pulse of lava comes in, it pushes the older volcanic rocks away from the vent, so it pushes it out. So in this case, the dome actually gets larger as more and more lava gets injected into the core of it, pushing out the outside. So think of it like blowing up a balloon. The more gas you put inside the balloon, the larger the balloon becomes. In the case of this eruption here, we have an explosive eruption. So this has produced what's called an eruption column, also sometimes referred to as a Plinian column. And so this column here is going to be made up of ash and dust produced by the explosive part of the volcanic eruption. So the volcano essentially explodes and sends a huge amount of fine material up into the atmosphere. And of course, this fine material is going to consist of pieces of pre-existing rock that got blown up during the explosion. That's going to be dust. But it's also going to consist of very small particles of lava that get thrown up into the air where they cool down and solidify, and that's going to be the ash. And we know, of course, basic physics, what goes up must come down, so we can see the explosion has sent material into the atmosphere, but we can also see over here the material is coming back down, then flowing down the side of the volcano. And you will see that the column itself is spreading out. As it gets higher into the atmosphere, the winds tend to push this material sideways, and it ends up producing this mushroom cloud-like appearance. Now, these explosive eruptions are most commonly associated with intermediate and felsic lavas because they have the highest volatile content. They have the most gas dissolved in the lava, and you need that gas to essentially come out of the lava in order to cause the explosion. In contrast, a mafic lava like this one here does have some gas in it, but nowhere near as much, and so it means that the explosive eruptions associated with mafic lavas tend to be very, very small, and you get something like this. When you compare that to something like an intermediate or felsic eruption, on the other hand, where you have an explosion, you will see it occurs on a much, much bigger scale because there's more gas involved. So now let's think about how gases affect magma. So let's begin by thinking about our bottle or can of Coke, which we've discussed in the past. Now, we know that the liquid inside an unopened bottle of Coke is homogeneous. It just consists of Coke. Now, we also know that within that Coke we have dissolved carbon dioxide gas, but that dissolved carbon dioxide gas can't escape the liquid because the pressure inside the bottle is too high. Now, when you open your can or bottle of Coke, you cause the pressure inside it to drop, and this means the carbon dioxide which is dissolved in the Coke can exit solution and form gas bubbles. Now, think of a situation, though, where we take our can of Coke or bottle of Coke, and before we open it, we shake it vigorously. Well, in that case, when we break the seal, what happens is we have a lot of gas exiting the Coke at the same time. And this causes a very, very big volume expansion, and this forces the Coke out of the can or the bottle under great force, and we see it forming this foam, because we have all this gas exiting very, very quickly. This is the same basic process that occurs during an explosive volcanic eruption. So here's the situation. Here's our volcano at the surface, and we know that the magma that feeds our volcano is going to come from a magma chamber down here underground. Now, when the magma is down here, it's under lots and lots of pressure because you have all of this rock pushing down on it. So down here, the magma is under lots of pressure, and the gases which are present in that magma cannot form discrete bubbles because the pressure is just too high. Now, as some of that magma exits the magma chamber and starts to rise towards the surface, the pressure begins to drop. And as the pressure begins to drop, we're initially going to see a few gas bubbles forming. And then as the pressure gets even lower, we're going to see even more gas bubbles forming, and these gas bubbles are also going to get larger. So if we have a situation where we have a very gas-rich magma moving towards the surface very quickly, and the gases which are dissolved in that magma manage to exit the magma very, very fast all at the same time, it means the volume of our magma is going to expand very, very quickly. And this is going to lead to an explosive eruption because this very, very rapid increase in volume is going to, number one, force the lava into the atmosphere very, very quickly. But the volume expansion is also going to damage the pre-existing rock, so it's going to blow it up because there's this huge increase in volume. So think of it like having a balloon and you're putting more and more air into the balloon. Eventually the balloon is going to pop. And that's exactly what we have here. We have this huge release of gas and the associated volume expansion, literally causing the volcano to pop at the top, throwing material into the atmosphere, which we see as an explosive eruption column. And of course, this explosive eruption column is going to consist of three things. There's going to be the ash, which are these small pieces of magma that get thrown into the air. We're going to have the dust, which is produced by the destruction of pre-existing volcanic rocks when the volcano explodes. And we're going to have gas as well, which comes from the volcanic eruption. And this gas is going to be hot. It's going to be several hundred Celsius in temperature. And so what we have here is we have a mixture of superheated gas, dust, and ash, which we see as an eruption column. So how does the viscosity actually affect the eruptions? Well, if we have a lava that's more viscous, it's going to find it difficult to flow away from the volcanic vent, and because it's so viscous, it means that the gases which get released by the lava are going to get trapped, and so the gas bubbles can't escape the lava before the lava solidifies, and so this means we're going to end up with a highly vesicular volcanic rock. Now, we've already discussed that the most likely types of lava to have this higher volatile content are going to be either felsic or intermediate in composition, because they have more dissolved water in them. And of course, in this situation, that dissolved water is going to exit the lava in the form of water vapor, so a gas. So when the water vapor exits the lava, obviously the gas bubbles that are produced find it very difficult to escape the lava because it's so sticky. And this means the volume of the lava begins to increase quite rapidly because the gas can't escape. And as we've just discussed, the faster this increase in volume occurs, the more likely we are to have an explosive eruption. So we can see in this situation here, we have ourselves a volcanic dome. So this is going to be a felsic eruption. So very, very sticky lava, which is absolutely stuffed with lots and lots of volatiles. And we can see that the eruption itself is resulting in this eruption column forming as the volcano begins to destroy itself due to the volume increase as the lava loses its gas. In contrast, lower viscosity lavas, and this is going to be mafic lavas, tend to have a lower gas content in the first place. But because they have this lower viscosity as well, it means the gas bubbles that form can escape the lava more easily. And so this means we don't get such a large volume increase as the gas exits the lava, because those gas bubbles that form can escape quite easily. And so the volume of lava doesn't increase anywhere near as much. And so this means we are less likely to get explosive volcanic eruptions associated with mafic lavas. We can end up forming lava fountains, which we saw a couple of slides ago, but in the grand scale of things, those are actually quite small and quite, gentle styles of volcanic eruptions. Compare that to, the kind of eruption that's going on here, which is extremely violent. So a lava fountain is nowhere near as violent and explosive as the kind of eruption that produces a eruption column. So you can see how viscosity and the amount of gas is going to affect the type of eruption that we get. And of course, the viscosity and the amount of gas we have is a reflection of the type of lava being erupted. So one more time, felsic and intermediate lavas, high viscosity, lots of dissolved gas, and so they're more likely to give us explosive eruptions. Whereas mafic lavas, lower viscosity, less volatiles, and so they are more likely to give us more gentle, less explosive eruptions. So they're more likely to produce lava flows rather than pyroclastic material. Okay, thank you for watching everybody, and have a good day.